So welcome everyone to my PhD thesis defense about data-driven methods for event cameras, from datasets to motion estimation and object detection. In this short dashcam video, you can see a pedestrian who's trying to cross the street. Unfortunately, the driver does not recognize this pedestrian in time, which leads to a crash. If we had a low latency perception system and accurate motion estimation, we could potentially avoid such casualties. One interesting sensor in such cases is the event camera. In this visualization, you can see a standard frame-based camera facing a rotating disk, as well as an event camera on the bottom. So the event camera forms a space-time spiral due to its high temporal resolution. If you now increase, or if you now stop the rotating disk, no events are generated, while a standard camera still emits regular frames. Now, if you increase the speed of the rotating disk, you'll see that a standard camera has a motion blur due to the exposure time, but due to the high temporal resolution of event cameras, we don't typically have motion blur in standard scenarios. Event cameras have certain qualities that we would like to exploit in this PhD. First of all, the low latency aspect of an event camera, typically less than 1 millisecond. The second, closely related property, is the high temporal resolution and limited motion blur. And finally, the high dynamic range, typically beyond 120 decibels. While we'd like to exploit these properties in this thesis, traditional vision algorithms are typically not able to be useful in this case. And this is because the nature of event data is asynchronous, and it does not contain absolute intensity information, but only informs about log intensity changes. In the last decade, the field of computer vision has changed dramatically since AlexNet won the ImageNet competition in 2012. Since then, deep learning has become a core part of computer vision and has also evolved over time. For example, 2015, we have seen ResNets. In 2017, transformers, and many, many more innovations that I'm not listing here. In 2018, the first work investigating deep learning for event cameras has been published, which is also around the start of my PhD. So you can see that the history of deep learning for event cameras is relatively nascent. In my PhD, I have asked the question, how can we combine the strengths of event cameras and deep learning for high-speed perception and robust motion estimation? This talk is split into 3 parts. First, I'm going to talk about the dataset foundation, then about motion estimation, and finally about representation learning for event cameras and object detection. So why are datasets so important for deep learning? This is because when we want to train neural networks on data, we need vast amounts of data to train them on. Unfortunately for us, if you want to work with event cameras, less than 1% of open source computer vision datasets have events as part of them. And of those, many are not designed to be useful for training neural networks. And this also limits the set of tasks we can look at or explore as researchers. But of course, there exist datasets even in event-based vision. Here I'm going to list a few of them. So for example, you can see the NCARS dataset, 1 megapixel, and DDD 17 and 20 dataset. There are some shortcomings here. For example, event camera resolution is typically very low, or they have no standard camera or no LiDAR, which is useful for low-level computer vision. Or there is no stereo setup, which could be useful for 3D vision. Published in 2018, is one of the seminal works in this domain. It features event camera stereo and standard camera stereo setup, as well as LiDAR. But in case of the driving scenes, the stereo baseline is a bit too small. And furthermore, not all sensors are hardware synchronized, which can lead to issues, especially for supervised training. So the goal with DSEC that I published in 2021 was to provide a high-quality dataset where we focus on accurate calibration and synchronization, and provide a stereo setup with up-to-date cameras, as well as a suitable baseline. And this dataset should also be useful for multimodal research. Here you can see the camera rig that we've built to collect this data. You can see that if you have a stereo rig of event cameras, and a stereo rig of global shutter RGB cameras, as well as a GNSS module and a LiDAR. One thing to note here is that we wanted to have a small baseline between the event camera and the standard camera to simplify multimodal tasks. But now the question is, of course, how do we calibrate such a multi-sensor system? But before that, we need to first quickly talk about temporal synchronization, which is also a key aspect of this dataset. So first, what it is, we have a GPS receiver that sends a pulse per second signal to the LiDAR and the microcontroller. And the microcontroller then sends trigger signals to the cameras so that all sensors have a common clock and we can synchronize them offline. Now we are ready to calibrate. But how do we do this? Because we have different modalities. We have event cameras and we have global shutter cameras. One very, very simple idea that works well in practice is to use image reconstruction with a neural network. What this does, it essentially synthesizes global shutter frames from events. And this makes it so that we are compatible with standard calibration frameworks. And we also show that this is a very accurate method in practice. So indeed, if we look at this overlay of events and the frame, you can see that far away we have pixel perfect alignment, but closer there's a slight misalignment, but this is actually due to the small baseline I mentioned earlier. So we went around in Switzerland for many months to collect this data set. Here you can see some examples on the Lake of Zurich and Lake of Thun. And overall, we then curated 1 hour of driving data in different scenes, so day, night, and HDR scenes, and also in different environments. We then used the LiDAR data to create depth or disparity ground truth and optical flow ground truth. But also other people have in the meantime contributed semantic segmentation, object detection ground truth. Now let's have a brief look on how this data set looks like. So on the top left, you can see the stereo event cameras, and on the bottom left, the stereo global shutter cameras. On the right, you can see the LiDAR, and here's a typical HDR scene where you can explore how we can combine these two modalities in challenging scenarios. What we also did is to train a neural network for stereo matching on events to see if you do a supervised training on this data set that we get a reasonable result. And I would argue that on top left, you can see the results. It looks something that we would expect from a stereo matching system, so confirming our hypothesis. Okay, now I'm going to talk briefly about data-driven motion estimation from events and frames, where you also make use of this data set. So first, let's have a look at this local space-time volume of events. If we warp this volume correctly, we can retrieve a sharp image of a human. And this indicates that motion can be extracted directly via warping, or in other words, we can directly estimate motion from event data. And this idea has been used extensively in the past for motion estimation from events. This is an example of a data-driven method where you have as input some events, you apply a neural network, you predict optical flow. And this is typically trained with this idea of warping, using the optical flow as well as the event to warp into a sharp image and optimize for the sharpness, meaning optimize for the flow. In practice, so at deployment time, this is very fast because we use a neural network. But there are some assumptions that are made. For example, constant illumination assumption because of the loss function that we use. And also there's only valid flow where events have been triggered. So in this context, I'm asking the research question, how can you predict dense optical flow that is also robust to illumination changes? A preliminary solution to this is to create a real-world data set and do supervised training in challenging scenarios. For example, we could train with non-constant illumination and with ground truth also at pixels where there are no events. And this is also what I first did. So I create a dataset extension, the DSEC flow, which features optical flow ground truth. And then I train a neural network on this optical flow. So how does this work in practice? So let's have a look. These are a few events that I'm displaying on the bottom. We can extract a short time window of events and compute a space-time tensor. So this is a three-dimensional quantized tensor where we can interpolate events into to retrieve the spatial temporal relationship between them. And this is very fast to compute and compatible with convolutional neural networks. We can even optimize for a good representation if you would like to. There are, of course, many other approaches to do this, but this is the one I used most in my PhD thesis. Indeed, we can also extract such a representation at any point in time that we want. And finally, we can predict optical flow from at any time. So here's an example of a neural network trained on DSEG flow. As you may notice, the output is not really something that we would expect from a neural network that is optimized to predict optical flow. You can also notice that there are these flashing street lamps, so I think at around 50 Hertz, which violate the constant illumination assumption. So the question I'm asking here is, how can we increase the signal to simplify the task for the neural network? And the idea that I propose here is to use a feature correlation approach. And this works the following way. So again, we extract event representations subsequently. So E1 and E0, that's time T0 and T1. And then the idea is here to use a feature matching approach. So in practice, this means we have a source feature and we want to compute the feature similarity between the source and the target feature. And the higher the feature similarity, also the dot product is, the better the match. So what this does is it exploits the static representation at time T0 and T1. And this is extensively used in image-based optical flow, but has not so far been investigated too much in has not been investigated at all in event-based research. In practice, to implement this idea in practice, I modify the raft architecture from the frame-based optical flow literature to support event data. So again, you can see these two event representations that we extract, and then we compute the correlation volume, which essentially does the feature matching between the reference and the target frame. But we also have this direct extraction of features from the most recent set of events. And this resembles the approach that I talked about earlier, where we directly extract features. This typically is more robust, for example, to occlusions. Then we use the update operator, so recurrent neural network, to predict the optical flow. Now in practice, the results look much better. So on the left, you can see the optical flow predictions from this neural network. And it is something that we would expect from this method. And even in these challenging scenes that I showed you earlier, so with this non-constant illumination, the network can predict a consistent flow. So now talking about the quantitative results, if you look at the baseline, for example, EV flow net here, if you use our approach to the ERAF, but without the correlation volume, we can even reduce the error by around 50%. But if we add now the correlation approach, we reduce that again by 34%, which confirms our hypothesis. And here you can see some HDR results, of course, because we use an event camera, we can exploit also that property, where RAFT, because it uses the global shutter frames, fails. But this is not due to RAFT, this is due to the camera limitation. But still, this does not fully exploit the high temporal resolution of events. And why is that? So let's recapitulate what we did. So again, let's look at a set of events. And we extracted two features, so the reference feature and the target feature, and we performed matching between those. If you visualize this in space-time, it's a straight arrow. But real-world motion is not cannot be represented by a straight arrow. Normally, it's a nonlinear motion in time. So the idea that I propose here to correctly regress nonlinear motion is to predict a polynomial curve, in this case, a Bezier curve for each single pixel. Now, by extracting intermediate representation between the reference and target time, we can exploit the high temporal resolution of event cameras and simplify the task. Because now we can use this to match features along the trajectory. And this is done in practice the following way. So again, you have the reference timestamp and the target timestamps, and we compute the feature correlation between the reference and the target ones so that the model can learn to match the features along the trajectory. It's also relatively straightforward to incorporate image information. So we retrieve a reference image and the target image, the features, and compute the same way the correlation between those at the different timestamps. Here you can see some results from this approach. So this was a neural network training simulation deployed on this real-world scenario, only using event data. And you can see that we are able to match or track pixels along large distances, which is very challenging for optical flow estimation. So in this last part, I'm going to talk about representation learning for object detection with event cameras. Representation learning is at the core of machine learning applications. And it also has been an active area of research for many years. But not only so for computer vision, but also for NLP. But these approaches are not directly suitable for event data. And why is that? We again look at a visualization of an event stream. You can see that information from events is spread over vast distances in space and time. So simply applying existing approaches fails in very complex tasks such as object detection. For example, if you now focus on the car again, you can see that it vanished in the event stream, and we will not be able to detect this object. So indeed, if you look at existing approaches on this chart, you can see MAP, which is a detection metric. So the higher the better, mean average precision, and inference time. This existing approaches typically require more than 40 milliseconds on a standard GPU. So they cannot exploit the low latency aspect of event cameras. Ideally, we would like to understand how can we improve performance while not taking too much time at inference. To answer this research question, I performed an extensive investigation. Sorry, maybe I missed the slide. So the question I'm asking here is, what are the ingredients for efficient feature extraction from sparse event data without sacrificing accuracy? And to answer this question, I performed an extensive investigation on efficient spatial-temporal neural network design. And the next slide quickly summarizes just the key findings from this study. So what I found is that it's crucial to use temporal recurrency. And this is because we need to propagate features in time even when no events are present. The second core component is the spatial feature aggregation. In this case, I used an efficient self-attention approach to aggregate features by maximizing the receptive field quickly. This is important because when you want to have a shallow neural network, you need to maximize the receptive field. And one key aspect here is that we separate the spatial and the temporal feature aggregation, which maximizes the efficiency. And then finally, we have a downsampling approach to enable hierarchical design. So how does this actually work in practice? So before we go to this, I call this the RVT, so recurrent vision transformer. And this is just a single block of the neural network. So first, we can again extract the representation from a local time window, compute a tensor out of this, and apply this block that I talked about earlier in a hierarchical fashion. We could then use any detection approach to detect objects. But more importantly, we also have a memory in the hierarchy. So we have memory on every single RVT block, which propagates information over time. So to come back to the same plot, the results are that we can do actually inference at less than 10 milliseconds while not sacrificing any accuracy. If we compile this neural network, we can even reduce it to 5 milliseconds or 3 milliseconds if you use a state-of-the-art GPU. So in the end, we are able to achieve low latency feature extraction while still achieving accurate object detection. And also at the moment, at the same time, keeping the design compact and simple. And I think this part is actually crucial for future research because it simplifies the understanding of what is useful and what works and what doesn't. So now let's have a quick look how this performs in practice. So in the middle, you can see the RVT, so the neural network that we designed. On the left, the feed-forward baseline, which struggles in this case where we have no events. And you can see that even over a long time, we can retain object detection performance. We also deployed this neural network on different sequences. For example, here, this is on DSEC. It was actually trained on a 1 megapixel dataset in Paris, but it also generalizes well to this scene. And finally, we deploy this model also in HDR scenes. And here we also increase the frequency to 80 Hertz. So we show that we can also overcome we can exploit low latency and HDR aspects of event cameras. So here I would like to conclude and show some takeaways. So the first is that I contributed a high quality real world data set that is suitable for training and evaluating neural networks in the wild. I showed that feature matching substantially improves optical flow estimation from events, and that they can be used to guide nonlinear motion estimation. And finally, that hierarchical RNNs can yield robust and efficient representations for low latency perception. At this point, I would like to thank everyone who has been involved in my PhD journey, especially David Escarmúzega for giving me the opportunity to do the PhD under his supervision, as well as all my colleagues, collaborators, and friends who have made this journey much more enjoyable. This is the list of contributions, and I'm up to questions. Thank you very much.